All right, welcome to the System Terminal. I'm your lead dev for this session, and today we are executing a complete system override on what a lot of people consider the absolute toughest boss battle in Cambridge Math 9709. I'm talking about logarithmic and exponential functions. Specifically, we're looking at how to transform nonlinear models into linear form. You know, we're treating this exam paper not as some unsolvable mystery, but as the target mainframe. It's literally just an algorithm. And today, I am going to give you the exact code, the exact syntax you need to jump straight from a B to an A star. We are bypassing all the superficial stuff and getting right into the source code of what the principal examiners actually want to see from you.
So here are our hackathon objectives for today. Number 1, the target mainframe. Number 2, core principles. 3, our debugging framework. 4, some beta testing. And 5, final code deployment. Let's get right to it.
Section 1. The target mainframe, the A-star difference. Let's initialize the simulation and meet our two junior coders for today's session, Dev Alex and Dev Sam.
Okay, what's really interesting here is the telemetry. When we look at the raw data from the Cambridge Assessment Framework, Alex's code represents your classic B student profile. He's incredibly fast with raw data inputs, but man, he causes massive memory leaks because of poor analytical depth. He just skips steps. Now, Sam, on the other hand, is absolutely brilliant at logic loops, but she completely fails the syntax rules. She always forgets to format her final answers correctly. To actually hit that A-star standard, Cambridge doesn't just want the final number spit out at the bottom of the page. They want to see connected, conceptual understanding. They literally want to read your logic, step by step.
But before we can patch this code and write our perfect script, we have to ask a really critical question. Why do so many systems crash during multi-stage analysis when transforming these specific functions? Like, why is this particular topic the one that causes memory leaks for so many candidates? Well, it comes down to cognitive load. You aren't just applying one simple rule here. You have to extract data, apply logarithms, manipulate algebra, map all of that to a straight-line graph, and then translate the gradient and y-intercept back into the original constants. It's a huge, multi-layered algorithm. And without a proper framework, it's incredibly easy to just drop a line of code and ruin the whole output.
Section 2. Core principles, the mathematical source code. All right, here are the raw data inputs we need to process today. The functions y equals kx to the power of n and y equals ka to the power of x. These are nonlinear curves. If you plot these raw, you get a curve, and it is notoriously difficult to accurately extract the constants k, n, or a from a curved line. So what's our system directive? We need to transform these equations into a linear form. You know, the classic straight line equation, y equals mx plus c. And we do this by taking logarithms of both sides. For example, for y equals kx to the power of n, logging both sides gives us log y equals n times log x plus log k. Boom! Suddenly our y-axis is log y, our x-axis is log x, our gradient m is simply the power n, and our y-intercept c is just log k. It is such an elegant, highly logical hack that completely simplifies how we visualize the data.
Section 3. Debugging framework, the command matrix.
Now that we actually know what we are transforming, Alex and Sam need a solid strategy. To clear the really strict Cambridge Assessment firewall, our developer team deploys this 5-step standardized sequence as pseudocode. We call this the command matrix. Step 1. Deconstruct the question. What exact variables are you given? Step 2. Extract relevant data. Pull those coordinates straight from the graph or the table. Step 3. Select your analytical framework. Are we using base 10 logs or natural logs? Step 4. Execute with clear notation. Look, this is exactly where Dev Alex usually fails. You absolutely must show the algebra step by step. And finally, step 5, present with correct terminology. Do not just leave your answer as a raw log value. Translate it back to the specific constants the question requested and to the correct number of significant figures.
Okay, before we compile this final patch and move into our testing phase, I need to halt the compile screen for just a second. To ensure your own personal operating system stays fully optimized for these exams, make sure you subscribe to Ace the Exams at Ace the Exams and turn on all notifications. We drop weekly system updates to provide you with the ultimate cheat codes for Cambridge exams. Make sure you're fully synced up.
Section 4. Beta testing, top 3 examiner warnings.
All right, we're resuming the session. Let's say we've encountered a logic error mid-argument while transforming an exponential function. What do? We check the principal examiner reports for known system bugs. The examiners literally publish a log of fatal syntax errors, and the absolute most crucial point is right here. These are the top 3 fatal errors straight from the examiners themselves. First up, confusing cause and effect. Students constantly mix up their variables after taking logs, so they end up plotting the wrong values on the x and y axes, which completely corrupts their gradient calculation. Second, forgetting format and presentation. You do all the hard math, but then you forget to state your final answer to 3 significant figures. You're just throwing away easy precision marks. And third, answers not specific to the context given. Like, if the question is about population growth over time, and you leave your final answer in terms of abstract x and y instead of t and p, the system will reject your answer. You absolutely must map the math back to reality.
Interactive beta testing arena. Let's run some immersive reader audits to see if you can spot the bugs. I want you to treat this like a live diagnostic.
Test 1 begins right now. Imagine you are on a real exam and you have a 60-second visual countdown clock ticking in your head when you look at a complex data chart. You're given a table of nonlinear data. You have exactly 60 seconds to decide your entire approach. Do you plot the raw data? Absolutely not. That causes a total system crash. Your immediate, instinctive response should be to generate a new row in that data table, calculating the logarithmic values for every single data point. Your speed in recognizing that you need to transform the data before plotting is the key to executing this algorithm efficiently.
Moving on to test 2, let's run a code review. Take a look at this comparison. On the left, we have a heavily flawed code block. The student has just written m equals 2, c equals 0.5, and jumped straight to k equals 3.16. Where is the working? How on earth did they resolve the logarithm? This completely fails to match the required analytical depth. Now look at the right. We have an optimized Cambridge standard code block. It explicitly states log k equals 0.5, it shows the actual inverse log operation, k equals 10 to the power of 0.5, and then it arrives at 3.16. It shows the machinery working under the hood. Top-scoring candidates always demonstrate evaluative thinking and justify their decisions with crystal clear mathematical evidence.
Section 5. Code Deployment. The Method Mark Strategy. And honestly, this brilliantly illustrates our ultimate fail-safe patch. This is a direct quote from the principal examiner report. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. Always, always show your working. Let's say you have a 5-mark question about transforming y equals k x to the power of n. 4 of those marks might be entirely for the process. Taking logs of both sides, that's a method mark. Equating the gradient to the power, method mark. Setting the y-intercept to log k, method mark. Method marks are rewarded for the process itself, and they can salvage your entire algorithm even if your final calculation crashes just because you hit the wrong button on your calculator. So please do not hide your code. Show every single step of your logic loop.
All right, we are officially logging off the mainframe. You now possess the exact code needed to hack logarithmic and exponential transformations. If this explainer upgraded your understanding today, make sure to subscribe to @Ace the Exams, click the bell for immediate system updates, and drop a comment below with your specific subject and level. But I want you to leave here with this one final thought. Logarithms aren't just some abstract button on a calculator. They are the ultimate decoding tool, capable of untangling the most chaotic exponential growth in the universe and forcing it into a perfectly predictable straight line. Stay analytical, keep showing your working, and I will see you in the next session. End transmission.